Okay, we left off talking about the what kind of ignition system?
Kettering.
Kettering, which uses a
Battery.
battery. And which aircraft uses this?
Some very new ones.
Well, maybe, perhaps, the Icon.
I
Yeah,
don't know that much detail.
not that much detail, but Tony was talking to me. So the Icon uses the Rotax what is it again? The
IS, 9.
IS, yeah, which I think is all FADAC controlled, electronic ignition, everything computer controlled. So it's more like an automobile. So it probably runs really well, doesn't it?
Yeah, it usually does pretty well.
Yeah.
You lose the battery and both the alternators, and you're done.
I went to Rotax school about a year ago, and I at that point I knew very, very little about Rotax. I hadn't been out when I was in the field, and I will just say that they're an amazing machine. And I was rather blown away at what they are internally and how they build them. I'm like, really?
Are they not piston?
Oh yeah, they're pistons, but they're just so different. I mean, every.
They use them in snowmobiles. We at work I saw it all the time when I was.
That's what I call them.
The ski resort. They're just like.
Right.
Yep.
That's where
every
they started.
single one
They
of
started
them
in
had a road
snowmobile.
tax.
Yeah.
And then
Yeah.
they started using them in, ultralights and.
Yep. So, yeah, very amazing little machines. A little bit temperamental,
Yeah.
but anyway. Yeah, they're just put together so different. Like we use single piece crankshafts. They don't. They press their cranks together and they're all
Really?
different pieces and stuff. And yeah, and anyway. So okay, back to this. So we're talking about the Kettering ignition system, which is a battery system to get us going, so we can understand the magneto system. And then we were writing some notes about said battery / Kettering ignition system, and we had gotten to this point when it was time to go. So just as a refresher, we'll go back to the drawing. So what happens is the battery supplies voltage current to a primary winding, which goes through points and back to ground and back around. And that charges up the primary winding, which makes it a electromagnet. So it has a field that grows and cuts across the secondary coil. Now it's held there, and that's not when it sparked. When it went out, it's going to spark when the cam, which is driven off of the camshaft, see, cam and cam, not hard to remember. Cam is driven off the cam, opens the breaker points. Then what happens to the primary field?
Collapses.
Wham! Really fast. So we had an electromagnetic field with lines of flux that were cutting across the secondary. So we have a rapid collapse of the primary across the secondary, which induced a voltage in the secondary, which finds its way through the distributor cap, spark plugs, back to ground, and around. The purpose of the capacitor / condenser is to
Aid in closing
Prevent arcing of the contact
that magnetic field.
two things: aid in collapsing and
Prevent
arcing.
prevent arcing across the points. Okay. So where we left off in our notes was rapid collapse of the primary induces 12 to 40,000 volts in the secondary, and I think I mentioned this. What dictates how much voltage you actually end up getting?
The ratio of windings. The gap.
Couple of things. One, it is the ratio of windings, but more importantly, it's the gap of the spark plug. If you don't have a gap, it's not really going to build up all that much. The bigger the gap, the more voltage you're going to get. So the maximum voltage would be the point right before it can't jump it. So it's going to build up till it has to jump the gap, jump it, dissipates all the electricity. Done. So, all right. Yeah.
That point that's building up, is that those two pieces that smash shut and start the second winding, or the second coil? Like, is that a gap for that piece?
That's a spark plug gap,
Oh, okay, that's a spark.
which is about 0.016, 0.018 on a spark plug, but because it's in a cylinder that is pressurized air, you're packing a bunch of air molecules into that little tiny gap, which makes it look electrically like it's much bigger.
Is that the little toy with the electrical things that's actually on our canvas for this class that has like the electrical? It's like a little glass ball with like a.
Oh yeah, yeah.
Is that because that thing is
What's that
in a
thing called?
vacuum?
I don't
And it's
know.
low voltage, and then the voltage can jump across. Is
I've
that
always
what
wondered
that's-
why that. You put your hand on it and a little.
They all go to
Oh,
yeah. Yeah, I'm kind of like wondering, is that the opposite? Like in a vacuum, does the spark doesn't need a lot of voltage for it to jump?
I don't know. I've always wondered. Why don't you get shocked? It's kind of cool. Maybe.
Probably because the higher
Yeah.
altitudes you have voltage leak.
Yeah. So vacuum would work. All right. So let me see. Where did we leave off here? The rapid collapse, voltage travel. Okay. So we have a rapid collapse of the primary, which induced a lot of volts in the secondary. Let's see. What was it? Voltage travels of the current. The current with the high voltage, because it wouldn't make sense to say the voltage travels. So the current travels via a large wire, because it's a lot of voltage, to the distributor, to that distributor. Distributor is driven off the same shaft the breaker cam is and points to the cylinder that needs to be fired. So the distributor is driven off the same shaft. That's not going to work out. Nope, I didn't think so. Driven off the same shaft. Oop. Hang on. I'm getting there. Same shaft as the cam. And points to the cylinder that is to fire. Which I'm going to come over here. I'll go back to that in just a second. Which is to say we have a distributor right here. So this little finger right there is pointing to the cylinder that needs to fire. And that's just going to rotate the same speed as the cam. When it's time to fire that one fires, then that one, then that one, then that one. And we'll get more into that in just a little bit. But that is the distributor. It has to go around and point to the right cylinder. If it's not pointing to the right cylinder, then the wrong one's going to get the spark, and that's going to make a mess. Let's see, we have a condenser. Condenser, also called capacitor, is installed parallel to the points. When I say points, the proper term I guess would be breaker points, but I would just say points. And then we save time, see world. Points. Yes. What do the points do? Sorry, not the points. The condenser. The condenser gives current. An alternate path. Alternate path. To keep points from arcing and helps collapse the field. That's not it. This isn't going to work out. Oops, what did I say? Collapse. That's not gonna work out. Collapse the field. There we go. Collapse the field. Let's see. Process is obviously repeated. I'll throw this about this. Process is repeated for each cylinder. In the automotive world, automotive, boat, almost everything except for airplanes, I can actually write that. I wrote automotive. I'll just leave it at that. In automotive, I don't want to write this. The timing is advanced. Okay, so in aircraft, we have fixed timing. It's either or. It's either at top dead center or it's someplace before top dead center. So as the piston is coming up, it's either going to be several degrees before top dead center, around 25. It depends on the engine, depends on the model, but 25 is a good round number. Or it's going to be exactly at top dead center. The only time it's at top dead center is when we're starting. We'll get more into that. But in automotive, it's going to vary a lot. Well, now, modern automotive, I mean, it is run by a computer and that timing is just all over the place, right?
Valve train too.
Oh, that's right. Now they're moving the camshaft around and doing all kinds of stuff. But we go back to, a car that would have points and a condenser, which would be what, 70s?
50s.
Nah, well, yeah. When did we leave? When did we stop doing points and condensers? It had to be about
Probably in the 70s.
in the 80s, you think?
They let the
Well,
all
yeah.
type sensors inside the distributors, I think.
Yeah, I have an 85 Mastercraft, and that still uses, well, it was converted to, but it would have still used points and condensers. But so figure somewhere around the 80s, they left this stuff. So, when you used to say, hey, you got to take the car in for a tune-up, right? I don't know if you still say that, but, what's a tune-up these days? Oil change, right? And then you change spark plugs every 100,000. So there's not much more to that. Oh, yeah, you put in, a new air filter or something like that. But, back in the day, it was a tune-up. You got new points and condensers, and then adjusted the timing. You did it all the time. You would put it on a machine. You would check all kinds of stuff, dwell time, and how long the points are open, how long they're closed. When it's, you put it on an oscilloscope. You look at the whole thing. It's kind of cool, but we don't do that anymore. At least not that I'm aware of. But anyway, so you would actually have timing would be advanced. So let me see, at start and idle and low power, it would be somewhat retarded, closer to top dead center. And then as you would advance and you wanted more power and the engine sped up, it would also advance, right? I'm not saying anything wrong here. And so the way they did that back in the olden days was pretty much two different ways. One would be you'd have a vacuum advance, because off of your intake manifold, which we're going to have to learn a lot about next year, is that your intake, it's between the carburetor and your intake pipes, it's actually a vacuum. So at an idle, that is a vacuum, just like your vacuum cleaner at home. I mean, if you punched a hole in it, it's going to suck a lot. And then as you accelerate, a throttle plate opens up and the air in there gets closer to what we have here, atmospheric, right? So that the pressure increases. So by using that vacuum on a little plate, it could rotate the plate, and that little plate rotating would actually make the cam either open up earlier or open up later. And that's how you would adjust the timing on these particular things. Or you could use a flyweight assembly where the faster it goes, the more centrifugal force you had, which would cause some flyweights to cause a plate to move, which would then make that little cam rotate a little bit faster. I don't want to say a little bit faster. In relation to its fixed spot on the drive shaft, it would move just a little bit more and give you some advanced timing. So we don't do that in aviation, except for if you're using electronic ignition. Now they're starting to do that. And I'm pretty sure, I think the Rotax does it.
They tried to do a vacuum advance?
Oh no, yeah, vacuum advance. So
you're
like the
saying
Surefly.
The vacuum advance at atmospheric pressure would retard the timing, and then once it built up.
No, what you would do, it's like the Surefly magneto has the option to run a line from the basically it's a magneto, but it's not because it's just an electronic box to sense manifold pressure. So it has and also it's obviously picking up speed because it's driven off a gear, so it knows the speed and the manifold pressure. So with those two things, it can advance itself. It'll know when it's starting for retard. It'll know when it's running fast for an advance.
So they don't
So
have
the
like
higher your vacuum, the more delayed it will be, but the lower your vacuum, it would be more advanced, correct?
So the slower the engine, the more the vacuum is.
Mm-hmm.
The lower that's called low manifold pressure, and the more advanced the throttle is, the higher the manifold pressure.
And that's
Oh,
when
manifold
you
pressure goes up as your engine speed goes up.
because your butterfly.
Okay, so this is a tricky one. And who's flown with me? And I talked about that.
Yeah.
It makes a little more sense when you're flying, doesn't it?
Yeah.
All right, and I don't want to get too far off the subject here, but it is important, and you do have to learn this at some point. So in your plane with a fixed pitch propeller, you don't have a manifold pressure gauge because you don't. It's pointless. It's like, why add the weight? It doesn't do anything. But as you pull the throttle back, and the throttle plate is closed because you've got a hole and the throttle plate closes, and it's pretty well closed, and these pistons are running and they want air, so they're syringes, they're trying to pull back and get air, but the entrance is blocked off. There's just a little tiny place for it to squeak by, so everything between that plate and the cylinder where it's pulling back, it's gonna be a huge vacuum, right? Okay, as you open the throttle plate and you get to go to wide open throttle where the throttle plate is like this, it offers just a very small restriction. And so now you have the pistons pulling back, the air coming in, and you have just a little bit of a restriction. So the atmospheric pressure on a standard day is 29.92, call it 30 inches. You're going to lose about 1 inch, so your manifold pressure is about 30, so we're at 29 inches. As where with an aircraft with a constant speed prop, we manage the power based upon RPM and manifold pressure. You're controlling both things. So like when I take off, I'm going to have my prop all the way flat into high pitch, and it's going to go right up to the stops, high RPM stops, and it's going to hit red line. I mean, that fast. Boom. My red line's 2400. It's going to go right at 2400 as soon as I add the throttle. And it's going to hold itself right at 2400. And I'll have the throttle all the way in, and it'll go well past, I have a green arc, so it'll go right up to almost 29 inches because it's non-turbocharged. And if I'm just going to stay here and stay in the pattern, I'm going to come up, and then I'm going to reach over and I'm going to pull back the throttle. But because now I'm flying and the way it works, my RPM is not going to change.
Yeah, it stayed the same like the whole time.
So I'm going to reach the throttle and pull it back, and the only thing that's going to happen is manifold pressure is going to start lowering down. Why? Because I'm closing the throttle. So now I have less pressure in the cylinders. Less pressure in the cylinders means lower horsepower. If you probably didn't notice, but there's even a little readout that says percent horsepower. All right, so as soon as I pull my throttle back, I'll pull it back, if I'm just flying kind of low, I'll pull it back to just about 20 inches. So I'll go from 29 all the way to 20. You'll see the manifold drop and the horsepower goes down. There's an indicator, you don't so much notice it, I mean, you can hear it. And then I'll reach over and I'll pull the propeller back, and I'll start pulling the prop back, and you'll see the RPM go from 2400, and I'll bring it up to 21. So it just happens, it's like coincidence, but it just works out. So you can go 21 inches of manifold, 2100 RPM, we call it flying 21 squared. And so as you do, then you'll be flying 21 and 21. So one knob's RPM, the other one's manifold. That was probably very confusing, but we'll go over it many times. And at some point, if you want, I'll just take you into the simulator. We'll just fly a sim right here, and I've had classes in there. We'll just, fly around on the simulator, and I'll show you how it works.
That'd be cool.
Anyway, all that to say, we don't advance our timing unless we have like a Surefly or something, which is a STC. All right.
Less parts to break.
Less parts to break for sure. I'm not going to write all that I had on here about spark advance, because I just wasted a bunch of time on it. I wasn't wasted. It's good to know. Automotive, use timing is advanced by use of flyweights or vacuum advance. In essence, the cam and distributor finger are rotated to fire earlier in rotation the camshaft position. You want me to write that? We're good? Okay, we're good. Oh, yeah, you got that. All right. There are some dangers. So, and this is good to know even in airplanes, especially in airplanes, really. A spark advanced at startup will cause kickback. So as we're rotating the engine with the starter, trying to start it, the piston is coming up towards top dead center, and it's normally set to fire, say, 25 degrees of crankshaft rotation before it gets there. Well, if it's coming up slow and it fires there, it'll kick back the other way. We need that piston to come to the top and start to come back around before it fires to push it down. If it kicks back, especially with Continentals, it can destroy the starter adapter and just blow it up.
Is that where backfire coming from?
No, backfire is, well, remember there's a difference in backfire and afterfire. Afterfire is out the tailpipe, and backfire is going out through the intake.
Well, I just think that because you're talking about it kicking back, it kicks back, it opens up that intake valve. No?
Yeah, could, yeah.
Okay.
Yeah. I don't really think, it doesn't really, it just, you see it kick back and you hear a bad noise and you're like, oop, that was expensive. Cause, that's supposed to be cause, C-A-U-S-E, cause kickback. Let me see. Spark advance. Too high a spark advance will cause detonation. What is detonation in cars?
Really bad.
Well, I mean, what do you call that?
It combusts too late in the cylinder, in the cycle? When the combustion happens too late in the cycle?
No, too early.
Early.
But what detonation? What do we call that in a car?
Oh, yeah. Oh, yeah.
There's a word.
A new window.
Pinging.
Oh, yeah. Knocking?
Pinging, knocking. Yeah.
Knocking
So
is when you're like not rock.
No, it's also
that's one of my favorite memes.
Okay.
Knock, knock. Who's there? Number 4 rod. It's like
Yeah.
sticking out there. So knocking and pinging in our cars, we have knock sensors that can hear that, and the computer will back out on the advance. We don't have that in airplanes because our timing is set. We don't have knock sensors, and not only that, we can't hear the pinging at all. So detonation, pinging in an aircraft is a huge deal. It can destroy an engine in less than 1 minute. So you put a magneto on wrong, you set it up wrong, you send it off, you could be buying an engine in less than a minute, assuming the pilot makes it back around. If they make it back around and land and like, hey, now I'm getting super high EGT temps, I got metal in the oil, I've got all this, what happened? You're like, oops, I accidentally mistimed the mag. That's okay. You just need to buy a new engine. And have we talked about the price of a nice 6-cylinder engine these days?
Isn't it like something like 80,000?
Yeah, you're skewing 80 grand for a 6-cylinder these days.
Just build a custom.
If it's a turbocharged, fuel injected, I mean, you could get into 100 grand for an engine now. So, yeah, that's a. All right.
Did you have insurance for that?
Well, I would imagine if you run a shop, you're going to have some fucking serious issues.
You would have
So, retarded spark
Blame the customer.
is inefficient. So if you think for a minute that you're just going to go, well, I'm just going to, I'll just make it really retarded. No, then it's going to be super inefficient and you're going to have problems. It's IN. Inefficient, thank you. All right, let's now move on and talk about the magneto.
pre-ignition and detonation.
Okay, so pre-ignition means that the ignition event happened before you wanted it to. That can be caused by a hot spot or something in the cylinder that lit off the fuel too early.
So it would be like essentially like your timing is not advanced, but something is pre-igniting it.
Yeah.
So it's not your time. The timing may not necessarily.
I think
be
technically that would be the timing and not be an issue. Although I will use it that way sometimes. Well, that was, that mag is mistimed, so it caused pre-ignition. But
and then detonation is when you're
That's
actually putting forces back, like you're
Yeah.
opposing the reciprocal.
okay, so detonation is this. When a cylinder combusts
That was
like
the
that,
detonation out there?
yes, when the fuel burns, it's an even burn with a heating effect, and it heats up not only does that burn and expand the air, but gases get hot, and it would be like me trying to move this over there by coming up and just pushing on the table. All right, detonation would be moving the table across this with a 20-pound sledgehammer, blow by blow. It's the exact same thing. So it's rather than a push on the cylinder, it's a gigantic hammer going down. And so it destroys everything. It's the bearings, it melts the piston. It is super bad. Super bad. All right, let's talk about this magneto. Let me see. I want a specific thing here. Where's my specific thing? My specific one. Okay, because I don't want to screw it up. So magneto. Let's just go through the whole thing and then we can write stuff about it later. How's that sound? All right, we'll start here. So the first thing the magneto has, there are 3 circuits to a magneto. Circuit 1 is
Magnetic.
circuit 2,
Primary.
circuit 3.
Secondary.
So it's magnetic, primary, secondary. 3 circuits. And the parts in each are going to look like this. Let's see. So the first thing we're going to have is a perfectly round rotor with magnets in it, north-south. Again, we'll write more stuff about this later. This is a 2-pole, single pole, north-south. You can have multiple poles. You can have north-south, north-south. That'd be a 4-pole. Just depends on what the manufacturer wants. So we have 1, a rotating magnet. 2, we have pole shoes. And, nobody's got this right, pole shoe extensions. So there are 4 things in the magnetic circuit. There are
Magnets.
rotating magnet. We say rotating magnet, pole shoes, and
Pole shoe extension.
pole shoe extensions. These are the extensions right here. Just the part that sticks out. Pole shoe extensions. And then we have
Soft iron core.
soft iron core. And all of that is laminated, made out of laminated iron, which we will get into. All right. Then we have the primary circuit. So, let's see. I may regret how I'm doing this. We'll see. Primary circuit. So the primary circuit is made up of
A primary winding.
a primary winding. Let's see, primary winding. Let's see, we'll go this way. Primary winding, which is going to go to,
The set of breaker points.
okay, set of breaker points.
Would it be cammed breaker points or just breaker points?
You're not wrong to say it can't, but it's breaker points, I think would be the way to do it.
Okay.
So breaker points, and let me think, we got to do technically a capacitor in parallel with that. Let me see. So or we could tie them together and do one ground. That'd be fine. And then a cam. And if we wanted to, let me think, we could also do an ignition switch. So we've got the condenser, we've got the cam, we've got the breaker points, and we have the ignition switch. Unlike the battery ignition system, and this is critical to your health and those around you, when the switch is open, it is on. So open equals on. On and closed equals off. Which is to say, if that wire is missing or broken or damaged, this magneto is on. It takes a ground wire to turn it off. So any one of these magnetos right here that is a complete assembly does not have that wire turning it off. Therefore,
It'll stay on.
it is on. If I spin it fast enough, and this one's pretty stiff, it'll spark. You can put your finger over there, you'll feel it.
So,
Okay. So now we have our secondary circuit. Yeah?
Sure.
Okay. Secondary circuit. Secondary winding. So we're going to have, let's see, a lot of windings of fine wire, maybe 100 or so more.
It's like as thin as a hair.
100 times more.
Yeah,
It is 100 so more.
100 times more. That is going to not touch there. Come over to here. So what are the parts of the secondary then?
So we got the secondary one.
Secondary winding.
We got a distributor rotor.
Okay, we're gonna have our distributor rotor, which will represent like this, the rotor. Then the distributor itself, which goes to, we don't really call it a cap, it's just the distributor, which will go, so we have the distributor rotor, the distributor,
Plug leads.
and our plug leads. And our ignition leads is what we call them.
Ignition leads and our plugs.
Ignition leads go to a spark plug, which goes to ground. All right, follow so far?
there's also the ground on the secondary winding.
I did it. I grounded it right there. See the little dot?
I mean, if I look hard enough.
Yeah.
I'm glad.
If it makes you happy, I can go like this.
Yes.
Okay. So we know how the primary and secondary work because it's no different than we just looked at a minute ago or yesterday. But how it happens now changes a little bit. So let's start with just looking at the magnetic circuit. So if we took a look at the magnetic circuit all by itself, this magnet has two basic positions. That is full register and neutral. And neutral. There's my full register, neutral demonstrator. This is my best one. All the parts have been removed out of this. It has two positions, full register and neutral. Neutral, this happens to be full register right here, so that's full register. And it's full register because the way it's set up right now, the lines of flux are going to come out of the north, travel around, through the core, back down, and into here. So we have the maximum concentration of magnetic lines of flux going through the coil core. And by the way, we do call it a coil assembly because it's made up of three things. The three things the coil assembly is made of is the
Primary and secondary.
core, the primary, the secondary. Okay. So remember how I told you gotta be super careful with these wires? You carried it by the wire. I don't look like it. But she's old. She's not gonna work anyway.
Snap.
All right. So full register. The opposite to that is the neutral position. So in the neutral position, we have the magnet going this way, like this, and the pole shoes going this way. Like that. And what the magnetic lines of flux are doing here is they're being short-circuited. So it's going to come around and go like this. So how much is going through the
Nothing.
Coil assembly.
coil assembly? We've got
Yeah.
nada.
Hopefully.
So it's all running around through like that, which is good. We're going to need that at some point. So if we took a look at this and we took a look at just the magnetic circuit, and okay, so when it is in neutral, it sticks. So if I get this anywhere and let go, it is going to find neutral. That's where it wants to be. Back it up a little bit. So I'm going to pass it around. You can play with it. It won't, there's nothing in there but that, so it's not going to like shock you.
I'll find a way.
I'll plug it in the wall, dang it. All right, so if we look at just the magnetic circuit and we look at what's happening with that, we're going to see something that looks, well, exactly like this. Oh, what is that?
AC.
It's gone.
We don't know because it went away.
It's the disappearing line.
It's a disappearing line. Now we'll have to wonder what happened to it.
So we went from 120 to 0.
You stay. All right. So there we go. And this being
0.
the zero position, which means there is
0.
no magnetic lines of flux flowing through the
Or
coil core. Best if we just talk about the coil core, because you always have something going through the pole shoes, right? It's going through the pole shoes here. It's going through the pole shoes there. That doesn't matter. It's all about the coil core. So we have nothing going through the coil core. So what it's representing is at one point, it's going to look like this. North is on this side. North is on this side and south is there the way I've got it drawn. Then, of course, it's going to come around. Then we're going to have south over here and north over here, right? Which represents going down below the line. Follow? All right. It doesn't matter which way is north and south. It's just this is swinging one way and that's swinging the other. It's go this way and that way and this way and that way. So all by itself, that is called the static flux curve. Static flux curve. Let's see. I think I have a drawing. A thing. Let me see. This one? This one.
All by itself.
There we go. Static flux curve. See, I was right. Static flux curve.
So neutral, there's no lines of flux going through it.
Right? That's 0. This is neutral. Neutral right there. Right there. That's neutral. See neutral? Nothing, right? Okay. And remember, we're talking about change. We want change to happen. So that's all fine and well. But then we're going to build on top of this some coils of wire. Yeah? All right. So remember Lenny?
When's
Yeah. Lenny? I called him Lenny back in the day. So we have Lenny involved in this. So what happens when we add Lenny is we have this coil of wire that's going to be built up across here. And as the lines of flux go through the coil core, those lines of flux radiate out, right? Okay, they radiate out. What are they doing when they radiate out?
Creating inductance.
Going through the winding.
You got to say it cuts through the primary winding. Okay? Because that's what, when it crosses, they call it cuts through. So the lines of flux from the core that were created by the rotating magnet radiate, the lines of flux radiate out and cuts through the primary winding. When you have this magnetic lines of flux that is changing, so now we have movement building up across the primary core, what happens inside the primary core?
It's building its own magnetic field.
Current starts to flow inside of the primary. And what is the flow? Well, I don't think I have it drawn quite right to show you, but we have that. The point should be closed at this point, so we have a path right there. So ground through the windings, through this closed points right here, because they'd be closed at this point, or back around. See the current? Okay, so current is allowed to build up into the primary, and it's flowing. What does that do?
Builds up a magnetic field in the primary winding.
It sure does. But let's back up just a minute, even though I led you to that one. And we have current in an inductor that is building up. And Lenz's law, Lenny, says that creates
Resistance.
Electromotive force.
a
Yeah.
counter electromotive force, which tries to do what?
Push back.
Stop it from coming in. And how long does it do that for?
5
5 time constants, right? Okay. See, it's like, why would everybody know that? It takes a little while. It takes a little while for it to build up, but that's all fine and well. So it builds up, and then we get to this point right here, which is the peak. The peak of magnetic flux pushing from the magnetic flux, pushing out through the core, out across the primary. It's the absolute peak. And then it starts to fall off. Right? So our magnetic flux from the rotating magnet is now dying off. It's right here. It's on the dying off phase. It's dying off. So what starts to happen to the current in the primary?
Doesn't want to let it go.
It doesn't want to let it go.
Boom. Lenz says, nope, not yet. You got to hang out for a little bit. So because of Lenz's law, it's going to hang out a little bit. Got it? So it doesn't fall off with the magnetic circuit. It waits a little while, and it gets about to right here, which took it about 5 time constants. And we got to a point that is about 10 degrees past neutral, because this is neutral, right? So it's under a lot of tension right now, is the word that they like to use. A lot of tension, because what's happening is this magnet is now all the way down over here. You see where that is? I'll use a laser pointer. All the way down here is where that rotating magnet, it's gone through neutral, and it's already going the other way. And here's our primary way up here going, man, it's a long way to fall. And in a second, what it's going to start to do is follow it. But before we get to that point right there, something's going to happen. Something magical.
The breakthrough.
It's E-gap.
It's called E-gap. And when I say what happens at what is E-gap?
Efficiency gap.
All right, so E-gap, I'm going to write this down. Get a right pen. E-gap. That's your definition of E-gap. Yeah, it's called the efficiency gap, blah, blah, blah. E-gap is a number of degrees past neutral that the point's open. Done. Mic drop. That is. So I said, what's E gap? It is?
Degrees past neutral points open.
All right, we'll practice that. So we're all in unison. Number of degrees past neutral, which point's open. How many degrees is that? I don't know.
10 degrees. Between 10 plus or minus.
Oh, no, it depends on the magneto.
Yeah.
So don't say 10.
Oh, okay.
Don't say 10 plus or minus 4.
It's the main, it depends
Positive
on the
number.
Now, because now you're specifically talking about a Bendix S20 series magneto. Maybe it's different for a slick. Maybe it's different for the 1200 series. So, or the 3000s. So, just it's number of degrees past neutral points open. It's about 10 degrees. So that'll be fine. So, all right. So at 10 degrees, what happens at 10 degrees?
Points open.
E gap. So it's number of degrees past neutral that the points open. So we have this primary coil that has been hanging out. It's under a lot of tension because its driving force has left the building. It's gone so far as to join the other team. It's going backwards now, and this is still up here going, hey, where'd you go? All right, so points open, and this goes straight down.
It's kind of like a rubber band snapping.
Sure, rubber band snapping.
Kind of like a car waiting at a light. And then when it turns green. It
It's
goes.
like when you're fishing, right? And there you have a...
It's like what a magneto.
Okay, so what it's like... Yeah. It's like what a magneto does. So what happened right here at this line, right here?
Points open.
The polarity.
Points open, but what happened to the field of the
Collapsed.
primary?
The field
It collapsed. How quickly did it collapse?
Immediately.
5 time constants? No, how about immediate and sudden? All right. Because
Over it.
now we can put this back together a little bit and go back up here and say, okay, so we had the rotating magnet was in what position here?
Full register.
Full register, which is right up here. Full register, and then it's going to rotate around until it gets to neutral, and our primary is still right here. Well, all of this time right here, what the primary is doing, it has current flowing. And because the primary had current flowing, it built up a magnetic field. That magnetic field reached out and cut across the secondary. So here we have the primary has cut across the secondary, and it's out there, but we just got 10 degrees past neutral, so points open, and that the current in the primary suddenly and rapidly collapsed, which cut across the secondary. That's when it's important that it cut across. It wasn't important that it built up and cut across. It's important that now that it cut across going the opposite way, collapsing, which doesn't matter if it's a buildup or collapse, cutting is cutting. So it cut across that secondary, instantly inducing a very high voltage capability of in the neighborhood of 20 to 40,000 volts, which will then roll through the blue wire, because blue represents our secondary. It will, at that point, hopefully this distributor finger will be lining up to the correct cylinder. It will fire the spark plug, hopefully at the correct time. It depends on you putting this magneto on the engine correctly, firing. And there we have a complete path through the spark plugs. Oh, I'll go back to this because it's got the little laser. Through the spark plug, through the ground, back around, through the ground. There is the loop that it goes through. So we have a complete path. And then that is how that all works. We didn't really talk about the condenser, but the condenser serves the exact same purpose as it did in the battery ignition system. When the points start to open, and when do the points open?
At E gap.
At E gap. At E gap, which is number of degrees past neutral, the points open. As the points start to open, the resistance lowers, and as they open, you could get arcing across. We don't want that, so the electrons are tricked into going this way until this is open. It's too late. All right. If by some chance this is connected, then what happens is we have a path from here, around through here, and there. And so the magnet can rotate all it wants to, and the field builds up and collapses and builds up and collapses. And it never, ever rapidly opens, because when this opens, you lose the ground. And when you lose the ground, field collapses. But if the ignition switch is grounded, then you always have a path through ground, and it never cares what's happening right here. So that's why when the switch is closed, the system is off because the breaker points can't do anything. You can open all you want. Field's not going to rapidly collapse because it's got another ground, so it just kind of follows the magnet. And you never get that rapid buildup. So that is why that is like that. All right, that's a good point to take a break.
So the magnetic field creates a magnetic field that creates a magnetic field.
Yes! We should say that.